Parametric coordinates. What we're used to using on our number plane are what's known as rectangular coordinates. So sometimes they're called that. Not that we need to know that. But there is an alternative way of doing it, is coming up with what we call parametric coordinates. Now, Cartesian, which is what we're used to, is where the actual curve is described by an equation, and then the points, we have two numbers, an x value and a y value. Parametric is sort of the other way around, where we describe the curve with two equations, one for the x value, one for the y value, and then the point is just described by one number, which we can then substitute into both equations to come up with the coordinates. That number is known as the parameter. So y equals x squared. That's the Cartesian equation that we're used to seeing. X equals t on 2 and y equals t squared on 4 would be an example of parametric equations. There's the point minus 1, 1. Well, if I was to give it its parameter, it would be t equals negative 2. So that is simply the point t equals negative 2. If we substitute into the parametric equations, you'll see it works, because x it would equal negative 2 on 2, which is negative 1. Y would be negative 2 squared, 4 over 4, which is also 1. So that's the parameter, t, or negative 2 in this case. So down there, there's another point, minus 1/2 a quarter. It would have t equals negative 1 as its parameter. The origin, well, that would be t equals 0. Then there's t equals 1. And that one there, 1, 1, would be t equals 2. Now, how do you change from a set of parametrics to work out what the Cartesian equation is? Basically, you eliminate the parameter. So it's like simultaneous equations, if you like. So we've got this one. The curves, the x value is going to be 2t plus 1. The y value is going to be 3t minus 2. We want to show that that represents a straight line. So how do we do it? Well, I'll make t the subject in one of them and then substitute it into the other. So it's just like the substitution method for simultaneous equations. So I've got t equals 1/2 x minus 1. Substitute it into the y, and we end up with what we recognise to be the equation of a straight line. So that would be the line we're talking about. So yes, that does work. Ooh, this one's a bit more interesting. X equals 2 plus cos theta, y equals 1 plus sine theta. How on earth are we going to get rid of the theta? I sort of have to cheat here a little bit. You remember this relationship? You saw that in junior school, sine squared plus cos squared. There's always one, trig identities. Did we do that in Year 10? Some people are looking at it a bit, and others are going, yeah, don't worry, we will see it again when we look at trig. But I'm going to need that relationship to do this. Because I'll make cos theta the subject of the first one, and I'll make sine theta the subject of the second one, and then I'll take advantage of this relationship that I know. So, I've done the cos squared first. Cos squared theta would be x minus 2 squared. Sine squared theta would be y minus 1 squared. And so, oh, hang on, that's a circle. So it'd be, the centre I know would be 2, 1, and the radius would be 1. A much more interesting curve. First of all, we're going to complete a table of values. So the x value is going to be represented by sine theta. The y value is going to be represented by sine twice theta. And they want us to go from 0 up to 360. So I've gone every 30 degrees like they've asked me to do. There are the x and the y values already. I've worked those out. So we don't have to spend time now going, they're the points. So let's plot them. There's the first one, there's the next, and whoop, yep, slowly, whoop. What on earth is this shape going to be? Unless you're looking at the sheet, you've probably got no idea what this turns out to be. Of course, you could just plot more points in like you always do, but it actually works out to be, there's the shape. Very interesting shape. These coordinates, when we have them in terms of the angle, are what known as polar coordinates as well. It's another way of describing them. So what on earth is the equation of this curve? Well, I'm going to have to make use of a trig identity which you may or may not know, and that's that sine 2 theta is actually equal to 2 sine theta cos theta. Again, don't panic, we'll see it later. But, you know. Now, I want to substitute in then, but all I know is that x is sine theta, so I'll draw myself up a little triangle, and I know sine would be opposite over hypotenuse, so x over 1. Bit of Pythagoras, I could work out the third side would be the square root of 1 minus x squared. I can now substitute in for sine theta and cos theta. So sine theta would be x, cos theta would be the square root of 1 minus x squared. There's our equation. Y equals 2x square root of 1 minus x squared. Sort of. It's better if I square both sides, because the y equals won't get the whole graph, because you'll notice this is not a function. So it's only giving me half of the function, positive square root. So to bring out the full equation, I'll square both sides and then I'll get the plus or minus square root. And so expanding it out, there it is. 4x to the power of 4 minus 4x squared plus y squared is equal to 0. Oh, fancy. 5H. We'll have a go.